So we have been talking about field distributions and breakdown in various kinds of fields of different media. And we have mostly discussed breakdown under uniform field conditions. That is because it is easier to predict breakdown processes that would happen when we have uniform field conditions. But in practice, most of the time, you do not have uniform field conditions. And when you have non-uniform fields, the exact mechanism by which breakdown may progress and ultimately catastrophic failure might occur can be very complex. Now, we will read about the various processes that happen in non-uniform field conditions later. But the first thing that we do understand is that given an option, we would prefer the field to be as uniform as possible within the dielectric material. Think about it like this. Let's say you have a parallel plate capacitor and you put a dielectric material with a suitable permittivity and breakdown strength within the capacitor plates. Now, if you want to utilize the material to its fullest capability, you will continue to apply voltage across it, and the material will withstand that voltage, withstand the field stress that it experiences till it reaches its breakdown strength. At which point, if the field is uniform, you might be able to achieve quite high voltages across the capacitor plates. However, instead, if you have a non-uniform field, which is, as we have seen, which can be represented by a needle plate geometry, in that case, as you keep on increasing the voltage, the fields in most of the material may be quite low and well below the breakdown strength of the dielectric material. However, there may be one point, a very small region next to the needle tip, where the field will be very high because there will be local field intensification. And if, as we have seen earlier, we have discussed earlier, that even if within that small region, the breakdown, the fields applied, the fields experienced exceeds the exceeds the breakdown strength of the material, then partial discharge will occur. And when partial discharges occur by various processes that we will discuss later, degradation and deterioration of the neighboring material will proceed, and ultimately catastrophic failure will happen, which means I may have to stop raising the voltage at that point. So I will have to operate at voltages such that even that local field, enhanced local electric field, is not above dangerous levels. At that point, the rest of the material is very lowly stressed. They are nowhere stressed near its breakdown strength. So what is happening is that I am not being to utilize my material fully. I'm not being able to utilize the dielectric material fully, and the efficiency of my dielectric is determined by a small region where local field enhancement occurs. And therefore, I would like to reduce this situation. I would like to be able to raise the voltage as high as possible without having any local field enhancement. It's not just the average field that is important to me. Even if there is field intensification at a single point, that is detrimental, and I want to prevent that. And how do I prevent that? I prevent that through electric stress control. So I design my material, I design my insulation system in such a way that local field enhancement is minimized. So when I design such that I can control the local field intensification within my insulation system, I would have a uniform field, I would have best utilization of my dielectric material, and this process is called electric stress control. So if you wish to not have a non-uniform fields, you need to have a measure for the non-uniformity of the field. How non-uniform is the field? We will not be able to achieve perfect uniform fields, but how much can we let it be non-uniform? And when does it start getting dangerous? For that, we have what is called the Schweiger factor. Of course, it is named after the scientist who proposed it. And the Schweiger factor is nothing but, it is also called the field efficiency factor. The field efficiency factor is defined as eta equal to E mean by E max. E mean is the average value of the electric field. So if you scan the entire volume of the dielectric and take a mean of all the electric field at every point, you would get the E mean value, and this should be very close to the mean value for an average field, which is V by D. So if you did not have non-uniformity and you applied a voltage V across let's say capacitor plates, and you obtained a perfectly uniform distribution, the field would be constant everywhere, and that constant field would be equal to the mean value of the field, which is V by D. However, when you have a non-uniform field, the values will deviate from this mean value. You will not have a constant value, and anywhere within the volume, wherever you have the maximum value, that value is to be taken as Emax, because we are interested in local field intensification wherever it happens. And when I mention this, I should mention that the maximum electric field in an insulation system need not necessarily happen at a predestined point. In fact, it is very difficult to predict where the maximum value will occur. It need not appear at any of the electrodes, let alone at the high voltage electrodes. It may not even appear in the region where the distance between the electrodes is the smallest. So we would actually need to do a field computation to find out where the maximum field enhancement occurs. So be that as it may, so we define the field efficiency factor as the ratio of the mean electric field and the maximum electric field. So if your field is uniform, then the maximum electric field will be equal to the average value, and therefore the Schweiger factor will have a value of unity, or if you express in percentage, which is also done, it will have a value of 100%. So this is what we should aim at. We should try to have a value 1, failing which we should try to have values which are as close to unity as possible. As the fields becomes more and more non-uniform, the Schweiger factor reduces, and this fractional value will approach 0. Let us imagine that in the needle plate geometry that we considered, at the needle tip, the tip radius keeps on decreasing. As the tip radius is decreased, the needle becomes more pointed, so there will be more concentration of fill lines. So the flux density will be very high. Electric field at that point will be very high, and therefore the Schweiger factor will be very low. In the limit that that tip radius approaches 0, the Schweiger factor will approach 0, which is as non-uniform as can be. It will be infinitely non-uniform. So that is a situation which has to be avoided. I mean, we don't really need to consider a needle plate geometry. The needle in a needle plate geometry can represent any protrusion in your geometry where you have a high local field intensification, because you have a protrusion or you have an edge with very pointed edge. So if you have a needle with tip radius 0 or you have an edge with 0 radius, it's the same. You will have a Schweiger factor which approaches 0 and which is very, very dangerous. So what we would like to do is, we would like to design our insulation system such that uniform fields are available everywhere, and even if uniform fields are not available, wherever there is field intensification, the Emax should be as close to E field as possible. And one way to do this is by designing the electrodes. We can control the electrodes, we can choose electrode geometries appropriately such that the field is uniform. Now, in the laboratory, often for doing breakdown tests or to simulate certain experiments, there are certain common electrode arrangements which are used. For example, there are plate assemblies, there is rod plane gap, there is rod gap, there is sphere gap, there is sphere plane gap, there is the needle plane gap. So all kinds of assemblies are available, and these are used for various experiments. Now, if I were to ask you to choose from among this an electrode assembly which would give you the best field distribution, in the sense of the most uniform field distribution, which would you choose? I have a feeling that many of us would choose parallel plate geometry. And we too keep talking about ideal parallel plate capacitors, because ideal parallel plate capacitors behave very nicely, and it lets us understand what's going on. However, the moment you're saying ideal parallel plate capacitor, you are making an assumption. You are assuming that the capacitor plates are infinite. And in that scenario, certainly you will have a uniform field distribution between the capacitor plates. But in reality, you do not have infinite plates. I mean, yes, infinite plates can be a approximation when you have a very small gap distance between the two plates. But even then, at some point, these plates will be truncated. The plates are finite. And at the point where the plates are truncated, there will be a pointed corner. And we all know what happens at the edges of capacitor plates. We have fringing. So let's say these are our capacitor plates. So you expect the electric field distribution in the gap to be more or less like this, approximately uniform. However, when you look at the edges you're not going to have a nice distribution like this. You will have fringing. So at the edges, there will be a concentration of field lines, and that will depend upon the radius of curvature of the edges. So more pointed the edge, the smaller the radius, there will be a higher concentration of field line, and higher will be the local field intensification. And it may well exceed the dielectric breakdown strength of either the material, or maybe there is a flashover along the surface of the material because the air along the surface of the material breaks down. Now, what will happen is this will happen when you are nowhere close to the critical breakdown strength of the material, and the V by D, the V that you will achieve, will be very low. To avoid this, there have been proposals by various scientists to profile the parallel plates in such a way that the local field intensification can be minimized. It is not zero, it is not perfectly uniform, but maybe you will have uniform fields between the plates, and at the edges, the fields can be reduced. The enhancement cannot be completely prevented, but it can be minimized. And there are several such profiles which are available. There is the Rogowski profile, there is the Bruce profile, there's the border profile. I'm not going to discuss all of them, but I will discuss the Rogowski profile and how it makes sense. So let us look at the Rogowski profile. Rogowski proposed electrodes for uniform fields for axially symmetrical systems. And the profile that he proposed follows the analytical function which was first introduced by Maxwell. Z is equal to A by pi W plus 1 plus e to the power W, where W and Z are complex coordinates in the W and Z plane. This picture is taken from Kufel-Zingel, and the derivation is also taken from Kufel-Zingel's book on high voltage engineering fundamentals. So if you have W and Z as the complex values, so Z is equal to X plus IY and W is equal to U plus IV, you have a relation between X and Y and U and V. X is given by A by pi U plus 1 plus e to the power U cos V, and Y is equal to A by pi V plus e to the power U sin V. So this is what you have here, and you can assume two infinite parallel plates in the W plane. We're just trying to see from this figure what could be a good profile that I can fashion my electrodes along. My electrodes are parallel plate electrodes, but I want to kind of modulate the profile of these electrodes. So let us assume these parallel plates, infinite parallel plates, V is equal to plus minus pi. So this is V equal to plus pi. This is where you see the straight line, horizontal line, and this is V equal to minus pi. So these are the two plates. Let us assume that these are the two plates. And this looks good because if you look at the distribution, you can imagine that in this region between the two lines v equal to plus pi and v equal to minus pi, you see a lot of lines. You see an almost square grid. You can assume that this v equal to constant line. So this is v equal to plus pi, and all these horizontal lines which are parallel to this, let us assume that these are equipotential lines. So v equal to constant with minus pi less than v less than plus pi. So all the parallel lines between these two edges, let us assume that these are equipotential lines. In which case, the lines u equal to constant between minus infinity to plus infinity are perpendicular to the equipotentials that we have considered, the lines which we have considered to be equipotentials. So they could be considered to be filled lines. So in this region, we can assume that the v equal to constant lines are the equipotential lines and u equal to constants are the filled lines because they are perpendicular to each other. And what we need to do is we need to fashion our electrodes in such a way that they lie along one of these equipotentials. And we have chosen v equal to plus pi and v equal to minus pi to be these two equipotentials along which my electrodes lie. I'm considering this to be infinite. Now, if you look at the z plane, these lines appear in the z plane as equivalent to an electric field distribution for parallel plates which can no longer go up to infinity but which will be terminated at x equal to 0. So at this point, along this line x equal to 0, if you terminate the electrodes within this region, what you will have is you will have a perfectly uniform field distribution. So you will have uniform parallel plates along v equal to pi, v equal to minus pi, and you will truncate them at x equal to 0. We do not have a problem here because from minus infinity to x equal to 0, you will have a uniform field distribution. But if you terminate these here at the edges of v equal to minus pi and v equal to plus pi lines, there will be crowding of flux lines. And the crowding of flux lines appear to be very high. And that means there is always the possibility of breakdown. There is always the possibility that the local field enhancement at these 2 points are too high to be acceptable. So can we change that? So obviously, we would like this field. This field is acceptable to us, but this crowding is not acceptable to us. So we have to move from what we assumed. What did we assume? We assumed that the plates will be placed along v equal to pi and v equal to minus pi. We can no longer do this because this doesn't seem to be a good solution to the problem. Can we do better? Now, of course, you cannot choose this, but if you look at the equipotentials between minus pi and plus pi, they all seem to be quite nice. I mean, they all have a uniform field geometry. You have the fill lines perpendicular. You have a uniform field. The problem is at the edges. Now, there is a lot of crowding when at the edge of a plate which you would place at v equal to plus pi or v equal to minus pi. But as you move away, as you move further and further away from minus pi and plus pi towards the center, the crowding of the lines decrease. And therefore, if you cannot force the field to be exactly uniform, you would choose a value such that the field enhancement is less. It is reduced. It may not be perfect. And so, you can choose any of the lines which are closer to the center. So, equipotential lines of v equal to constant, which lie between minus pi and plus pi, seem to be better than the solution where the plates are at plus pi or minus pi. And Rogowski's profile of choice is that equipotential line for which cos v is equal to 0 or v is equal to plus minus pi by 2. These are the bold lines that are shown here, 0.5 pi. So I am going to fashion my electrodes not to be infinite parallel plates, but a parallel plate with this profile, with the profile of cos V equal to 0 or V equal to plus minus pi 2, where V is given by this, and U and V are given by these relations, and Z follows Maxwell's analytical function. So thus it was that this profile was obtained. This is also called Rogowski's 90-degree profile. With Rogowski's 90-degree profile, you can fashion your parallel plate geometry in such a way for an axisymmetric system that you get a very uniform field between the plates, and you get a reasonably uniform field, and you are reasonably able to control the stress at the electric stress at the edges of the plates. So this is what we do with the Rogowski profile.